Hello students, today I'm going to teach you very important part of vector linear algebra, that is vector space. And we see today what is the definition. We come across a lot of examples. So watch the video till the end and try to understand vector space, subspace, linear independent, linear dependent, linear combination. All these definitions we are going to study today, and which is helpful to solve the examples. Watch the video till the end. Thank you so much. Hello students, so we are going to start introduction to vector space. We just go through the applications, definitions and so on. Why to study vector space? What is its application? Is very important question for engineers, and they should know why it is important. So here I have the concept of vector application is fundamental in linear algebra because together with the concept of matrices, it allows the manipulation of the system of linear equation. Vector space generalize vectors and enable the modeling of physical quantities that have a direction and magnitude attached to them, such as force. So here we have the vectors itself is nothing but we can see we have a very large application saying that with the magnitude we have direction, that is, and in the space you can say with the direction ijk it gives us a vector space. So this is the application we have. Immediately we'll go to the definition of vector space. A vector space is defined as a vector space is a non-empty set V of objects called vectors on which are defined two operators, addition and multiplication by scalar or real number. Scalar means it is a real number, subject to the 10 axioms, or we say axioms as rules listed below. The axioms must hold for all the vectors u, v and w in V. For all scalars c and d, the sum of u and v denoted by is in V. So let us start the axioms. We see all these axioms must be proved, then the quantity whatever is given is a vector space we declare. Okay, so let us start with the axioms or the rules of vector space. So first one, it is u of v belonging to V. So closure under vector addition. So closure property satisfies. Then u of v is equal to v of u. It is a commutative law. It may be addition and it may be multiplication in this case. U of v of w is equal to v of u of w associative law satisfies. A fourth axiom is there exists an element 0 belonging to v called a zero vector. Yes, zero vector is also important, such that u of 0 is equal to u. So existence of additive identity is axiom is satisfied. For each u belonging to v, there exists an element minus u belonging to v such that u of minus u is equal to 0. So you can say existence of additive inverse is satisfied. For each u belonging to v, there is an element minus u belonging to v such that u of this is repeated. Okay, no problem, you'll understand. Then a of u belonging to v is closed under scalar multiplication, and for every u belonging to v, there is an element minus u belonging to v such that existence of additive inverse exists. Then we have a of u of v is equal to a of u of a of v is a distributive property satisfies. And the last property, that is identity property, that is 1 into u is equal to u belonging to v. So these 10 axioms must be satisfied, and we say the given vector is a vector space. So this is a very simple definition, and we have to find examples we come across this. So instead of here u, we will take this as v also. V is there, we can take this as instead of u, we can take v. So like this, u and v are the vector space. Now here we have the subspace ones, a non-empty subset w of a vector space v of f is said to form a subspace of v if w is also a vector space over f with the same addition and scalar multiplication as for v. So what it means, friends, please remember, whenever it come across the subspace, we say that there exists one subset which is non-empty, it should satisfy addition and scalar multiplication. Then we declare that w is a subspace. And how we test? This is a very simple idea I have given. To test for subspace, please remember the first condition, w must not be empty. It is a non-empty set. So what it contains? It contains from the vector space v, w is the subspace of v if it fulfills the three conditions. Very simple. First one, w contains a zero vector, u and v are defined w, then u plus v must be in w. Then we have next one, that is k is any scalar and u is contained in W, then ku must also be in W. So this three condition says that, and W is non-empty, we declare that W is a subspace, which is a vector space. So please remember this subspace definition, which is helpful while solving the examples. Examples we are going to solve in the next video lecture, and we see very important examples we are going to solve, which is important in the examination, students. So once again we just see how vector space is. So vector space is a fundamental concept in linear algebra, as I have discussed in the beginning of my video lecture, that linear algebra very vast applications we have, and vector space is a part of linear algebra, very important. It says that it's a mathematical structure that contains a set of vectors and two operators, vector addition and scalar multiplication, which satisfies the certain properties, and what these properties are is a set to be considered as a vector space. When these properties are satisfied, we say it is a vector space. What it says, a closure under addition. What's closure under addition? If you take any two vectors and their sum, or u plus v is also a vector space, then we say it is closed under addition. Similarly, we have vector under scalar multiplication. Okay, let us take one scalar which is a real and it forms the field. Suppose C is the scalar. In this case, any u is a vector space. The product C into u is also must be a vector space. Then we say it is closure under scalar multiplication. Next property says additive identity. Very simple, we have additive identity. As we have seen, 0 must be a vector space, and 0, if you consider with the vector space u plus 0 must be equal to u. So then we say it satisfies additive identity. Similarly, we have additive inverse. In this case, for every u in the vector space, there exists vector v such that u plus v must be 0. So we may say that how it is possible. So in this case, we can also take this as v equal to minus u. Yes, then we can say very easily, when v is minus u minus v, u is equal to 0, and it satisfies additive inverse. Associative of addition, how it is going to satisfy, students? Suppose there are three vectors u, v, w, then u plus v plus w is equal to u plus v plus w. In the bracket, it satisfies the associative of addition. Similarly, we have additive, just cut this part, commutative of addition. For any vector u and v in the vector space, u plus v is equal to v plus u. So commutative law is satisfied. The last property, that is distributive property. Scalar multiplication distribution over vector addition, and scalar addition distributes over scalar multiplication. This property we can easily see in the example. Similarly, we'll also understand subspace in a different way. A subspace is a subset of a vector space that is itself a vector space with respect to the same operations of vector addition and scalar multiplication. In other words, if you take a subset of a vector space, it should satisfy all the properties of vectors. From above, we can see the 7 properties what we have taken. It should satisfy all the vector space, and it's a subspace of that vector space. So if we just see how the subspace must be there, at least these 3 properties must be satisfied. One, it contains 0 vector. Second one, closure under addition, and closure under scalar multiplication. Suppose if you take a 0 vector, it should belong to vector space, so it contains the 0 vector. And then in closure addition, u plus b must belong to v, and in scalar multiplication, cu must belong to v. That's it. Suppose if you take the examples, a set of all real valued vectors in 3 dimensions, space is a vector space, because there are 3, and you can see very easily it satisfies 0 vector, closure under addition, closure under scalar multiplication. These examples again I will once again explain in my next video lecture. The next example is the set of all 2 cross 2 matrix with the real entries is a vector space. Yes, very easily we can identify. To take any matrix with 2 cross 2, there are 2 rows and 2 columns. We can very easily split this into 2 u plus v, and we can say that this belongs to the vector space, and it satisfies the property of additive in closure under addition. Similarly, if you take any constant c and multiply to the matrix 2 cross 2, we can very easily see c is multiplied to every element of the matrix, and it satisfies closure under scalar multiplication. And similarly, if you take any elements, you just take 0 vectors, so you can just 0 matrix we are going to take in the second example. 2 cross 2 0 matrix, we can say very easily that is 0 is easily added with the matrix and we get the vector space. So like this, it satisfies all the properties, therefore the 2 cross 2 matrix is a subspace of a vector space. Next example, the set of all solutions to homogeneous linear systems of equations forms a subspace of a vector space of all solutions. So immediately we can see very easily solutions what we find in the homogeneous linear system, they are subspace of vector space. This point is very very important. Please remember this point, students, because this I'm going to use in the examples. We get the linear systems and linear homogeneous equations we get. You find the solution. These solutions are the subspace of the vector space. So the solutions of equations, we say just solutions of equations as vector space, which are subspace. So remember that a subspace inherits its property from the parent vector space, but it is also a vector space in its own right. So some more examples I have taken. So real number space, the set of all n dimension vectors with real number components. For instance, R square consists of order pair x comma y, where x and y are real numbers, so x plus y is also satisfies the condition, x plus y is equal to y plus x also satisfies the condition. So like this, a real number space R raised to n is a vector space. Similarly, we have complex numbers similar to Rn, but the components of the vectors are complex numbers. Please consider the C3 consists of 3 order triple z1, z2, z3, and they are complex numbers which satisfies the vector space. So polynomial space, even polynomial equations we get, they satisfy the vector space. We can just see the quadratic polynomial, we get the coefficients which are the solutions of the quadratic polynomial. Just now I said that the equations or the homogeneous linear equations are there. One of the equations you can consider this as a quadratic polynomial is there. We get the solution. These solutions are the vector space because they are the subspace. It satisfies the conditions of subspace, so therefore we say that they are vector space. Then matrix space, yes, just now we discussed about 2 cross 2 matrix. Similarly, in general it is m cross n matrix with entries from a field. Then it consists of all 2 cross 3 matrices, and therefore it satisfies matrix. If you take any matrix, there is a vector space. Then function space, yes, the set of all functions that satisfies certain conditions. For example, all the continuous functions defined on certain intervals. Suppose you can take any sine function, cos function. Yes, they are all vector space because you can see the sine function, how it going to form the waveform. Cos function is there, how the waveform we get. When the tan we get very easily the waveform, which is direction and magnitude. It has the function and it satisfies the vector space. Then solution space of homogeneous equation. Yes, just now I declared that homogeneous equations, we get the solutions, we find the linear equation and we find the solutions for that, and we declare that this equation satisfies the vector space. Then it is also subspace of Rn. You can just say the subset of Rn that satisfies the properties of vector space is a subspace. Then trigonometric function space, yeah, just now I just said the set of all trigonometric functions that satisfies certain properties such as periodic, just say it as the satisfies the vector space. Vector space of continuous function is also a vector space. Vector space of sequence, the set of all sequence of real or complex numbers satisfies the certain conditions and therefore they are declared as vector space. So this is all about the vector space. We will move to the linear combination, students. So just we are going to take some V is a vector space over the field F and let V1, V2, Vn belong to V. Any vectors of the form V1, V1 plus A2, V2 plus dot 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 plus A and Vn belonging to V, declare that A1, A2 till An belong to F is called a linear combination of V1, V2 till Vn. So like this you remember how linear combination. Linear combination means it is a combination of a field and the vectors combination. Together they form the linear combination, which is a vector space again. So very important concept, a linear independent dependent basis in the vector space. So stay tuned to the video lecture till the end of this. Friends, we are going to finish this definition, then you'll come to know how to solve the examples. In my next video lecture, I'm going to solve examples on linear independent, dependent and basis, which is very very important in the examination purpose, friends. If you prepare for any type of examinations, definitely you're going to get these questions in the examination. So let us see what is linear independent. The set of all vectors v1, v2, vn in the vector space is said to be linearly independent if no vectors in the set can be written as a linear combination of the vectors. The very simple linear independent says that there are some scalars, okay, any scalars are there if they form the equations like c1 v1, here we have c1 v1 plus c2 v2, right, and till cn vn, they all equal to 0 holds only when c1 equal to c2 dot 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 cn is equal to 0, then the set of all vectors is linearly independent. What is linearly independent? Please remember this condition. First, there are scalars and they form the linear combination with the vectors using the definition of linear combination. what they say, all this will become 0 when you get the solutions. Am I right? Then when you get the solutions, when all the scalars c1 is equal to c2 dot 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 cn is equal to 0, then we say the given vector, the set of vectors is linearly independent and they have the solution. That is the meaning of linearly independent. Then we have basis. A base for a vector space is a set of vectors that is both linearly independent and spans the entire vector space. Yes, but the basis satisfies only two. Basis says that it must be linearly independent. Vector, a set of vectors must be linearly independent, and it spans means it is going to rotate or it's going to generate entire vector space. Then we say it is a basis. In other words, yes, a basis is a minimal set of vectors that can generate all the vectors in the vector space through linear combination. So each vector in the vector space can be uniquely expressed as a linear combination of a vector. Yes, then it forms basis for the vector. So remember this point. A vector set of vectors is a basis with first condition linearly independent. A second condition, it is a span the entire vector space. And the third condition is to generate all the vectors in the vector space. Then using linear combination. Using linear combination, it is going to generate all the vectors in the vector space, and then we say it is a basis for the vector. So a basis is a fundamental concept in linear algebra because it proves a way to understand the structure of a vector space. Yes, students, so very important. Why we study basis in the vector space? Because it is going to give the structure of the vector space. So they may be 2 dimension, 3 dimension, it may be matrix, it's a real number or complex. Its structure we can easily understand using the basis. So we have taken the number of vectors in the basis is called dimension of the vector space, right? So how many bases you have, and those many dimensions we can easily see in the vector space. So for example, R3, if you take, the standard basis is fixed, it will never change. Remember, standard basis is fixed. It consists of 3 linearly independent. So how we are going to say the vector I is equal to 1, 0, 0, j is equal to 0, 1, 0, and k is equal to 0, 0, 1. So this is the 3 directions, 3 dimension vector space, and it spans. It is linear combination we can find. Therefore, this is a standard basis. So note that linearly independent characterization, the relation between vectors in a set and a basis provides a fundamental framework for expressing all the vectors in the vector space. This is all about the basis. We move to the last part. I think we'll come across the definition of linearly dependent. Okay, one concept you should remember: linearly independent, linearly dependent. Linearly dependent says that the set of vectors v1 till v2 till vn is a vector space is said to be linearly dependent if there exists scalar c1, c2 till cn not all equal to 0. Not all equal to 0 such that the equation c1 v1 plus c2 v2 till cn vn equal to 0 holds. In other words, the vectors can be combined in a non-trivial way to yield the 0 vectors. Only one difference you can say in linearly independent and linearly dependent: all the scalars are equal to 0 linearly dependent. All the existing scalars are not 0, then we say it is linearly dependent. Independent, all scalars must be 0. Dependent, not all are 0. So this is linearly dependent and independent. So few examples: suppose vectors, if we take r square, then v1 is equal to 1, 0, v2 is equal to 0, 1. This 2 scalars is called as the standard basis vectors and are linearly independent. And then we have example 2, r3. If we just say u is equal to 1, 2, 3, v is equal to 4, 5, 6, these vectors are not scalar multiple of each other, so they are linearly independent. Example 3, you can just say r the polynomial p of x is equal to 2x square plus x minus 1, q of x is equal to 3x square plus 2x minus 2, and r of x is equal to x square minus 1 linearly independent. Let us see. Suppose if all the solutions, if you just write this equations in c1 p of x plus c2 q of x plus c3 r of x is equal to 0. Suppose the set of equations, you have to write these equations in your own. I have written in the linear combination of scalar multiple of vectors in polynomial. If you find the solutions c1, c2, c3, and if all the solutions are equal to 0, we say the linearly independent. Suppose if any one is not equal to 0, we say it as linearly dependent. So linearly independent and dependent. Check if the vectors are linearly independent. Suppose if you take a 1, 0, 1, b 0, 1, 0, and c 1, 1, 1, we can easily write this in linearly independent. So we just see the set of equations, that is linear combination always: c1a1, c1a plus c2b plus c3c is equal to 0. We can solve this, friends. c1 equal to c2 equal to c3 is equal to 0. So vectors are linearly independent. Similarly, we take another function f of x is equal to e raised to x, g of x is equal to sin x, and h of x is equal to cos x, linearly independent. Okay, the set of equations c1 f1 x. So we are going to take the linearly combination, and here we are going to take the solutions for c1, c2, c3, and we can see very easily the three constants or scalars c1, c2, c3 are 0. So the functions are linearly independent. So like this, students, we have solved so many examples, we have seen the definitions. If you like this video and if it is helpful for examination, please like and subscribe. And very important, from all these definitions and some of the examples and problems, we are going to solve the very important examples in my next video lectures. Please like and understand this concept in this video easily. The next video will be very easy. Thank you so much, friends. Stay tuned with the YouTube channel, and for more updates